Keeper 5.1 Linear Approximations. So the idea of a linear approximation is that I can take a tangent line to any curve and I can zoom in really, really close and I can make my graph look almost linear. So for instance, in this example, I have this curved piece of the graph, which is ln x. So again, the curved piece is ln x. And then I found my tangent line, and my tangent line is above the graph of ln x. Now when I zoom in close to where the tangent line hits the graph at 1, for example, so I zoom in right here, and I notice that those lines basically overlap each other, and even as I go out, so even at like 1.2, the lines are still pretty close to each other. It's a little difference, but it's not like a huge difference. So I can use the equation of a tangent line to approximate the curve, even though the equation of the tangent line isn't exactly the same. It will still give me a good approximation because visually, when I zoom in, my lines would be close to each other. Now, what's the purpose of that? The purpose of it is if you didn't have a calculator and you were trying to calculate, for instance, ln of 1.3, you probably can't do that in your head. But if I know my equation of my tangent line, I can calculate 1.3 because the equation of the tangent line is linear. All right, so here's our steps for finding the linear approximation using the equation of a tangent line. First, you're going to write the equation of the tangent line of the graph. Then you're going to solve the equation for y and replace that y with L of x. L of x stands for linear approximation. Finally, you're going to use your linear approximation to estimate or approximate the given value, whatever they ask for. Now, here's your formal formula for linear approximation. I don't actually use this formula, but if you had to, it's just basically the equation of the tangent line solve for y. So all I do, again, I don't necessarily use this formula. All I do is solve for y in my equation of my tangent line to get my L of x. All right, so here's our example. It says write the equation of the line tangent to the graph of f of x equals ln x at x equals 1. So I'm going to start by finding the derivative. So the derivative of ln x, we should all know by now, is 1 over x. Next, I'm going to find that derivative at 1. So f prime of 1 equals 1 over 1, which is 1. Now I need to find the y value at 1, so I'm going to do f of 1. And f of 1 is ln 1, which is 0. And then I can put that into my point slope form. Part B says solve the equation for part A for y and then replace y with L of x. Well, this one's actually pretty easy because our equation from part A was y minus 0. So I get y minus 0 equals 1 times x minus 1. Solving for y, I get y equals x minus 1. And again, instead of using y, I'm going to denote the linear approximation as L of x. So L of x equals x minus 1. And generally, this L that you see here, generally that's written as like a cursive L, not like a typed L. All right, part C says use that approximation that we found in part B to approximate f of 0.95. So I'm going to take my approximation. So again, remember our approximation was x minus 1. And I'm going to plug 0.95 in there. So L of 0.95 is 0.95 minus 1, which is negative 0.05. In other words, ln of 0.95 approximately equals negative 0.05. Part D says use the linear approximation to approximate 1.2. So again, I'm going to do the same thing. I'm going to plug in 1.2 into my formula. And so again, my formula is L of x equals x minus 1. Plugging in 1.2, I get 1.2 minus 1, or L of 1.2 is 0.2. Therefore, f of 1.2 approximately equals, or ln of 1.2 approximately equals 0.2. Now, please understand, I can do this to approximate any number, but since I used 1 in the initial question, since we were using x equals 1, that was the initial x value they gave us, I only want to choose values that are close to 1. Like, I wouldn't want to choose 2. All right, 2 would be too far away from 1, and the equation of my tangent line would not give me a close enough approximation to the answer. All right, part D says, well, let's compare it. Let's look at the real answer for 1.2 and compare it to our approximation. So remember from part D, we found that f of 1.2 was ln of 1.2, which we found to approximately equal 0.2. Now, to find the actual answer for f of 1.2, you would need a calculator. So I'm going to get my calculator out, and I'm going to type in ln of 1.2. All right, when I plug in ln of 1.2 into my calculator, I get ln of 1.2 equals 0.1823. Now you can see that our approximation of 0.2 is very, very close to the actual answer of 0.1823. And so, again, our approximation we can see is an overestimate of the true value because it's bigger than the true value, and it's an overestimate of that true value by 0.0177. So it wasn't too far off. All right, the last part of this, we want to think about that graphically. Now, remember, we just concluded that it was an overestimate because we found the actual answer. But even if I hadn't found the actual answer, I could determine that it was for sure going to be an overestimate. And the way that I know that it's an overestimate is because my graph of ln is increasing and is concave down. That means when I draw the equation of the tangent line, by default, the equation of the tangent line has to be above the function. It's going to bump off the function and go off to infinity, whereas the function is curving while going off to infinity. So simply stated, to answer this question, is it an over estimate or underestimate, and why is this? I would say something like the tangent line is above the graph, therefore the approximation has to be an overestimate because the equation of the tangent line is higher. Additionally, because the graph is concave down at x equals 1.2, the tangent line must be above it, again telling us that it must be an overestimate.